Okay, so we are talking about momentum today. Momentum is part of a lot of Isaac Newton's original theories. It's actually a major part in many of them. Um, it has an interesting definition, though. When he first came up with momentum, Newton said he defined it as an object's quantity of motion. It is its quantity of motion. Okay, well, that's cool, but I feel like it's kind of a vague definition, right? How do you quantify something's motion? Well, let's use an example to talk about this. Let's say we got two people and they're playing catch. Let's say that the one person's holding, let's make it an apple. There you go. It's kind of an apple. And that person throws the apple to the other person, and the other person has to catch that apple. Now, if they were to throw it relatively softly, it'd be easy to catch. But if they were to then throw that apple at twice the speed or four times the speed, way faster, that would make the apple a lot harder to catch. So if we were to quantify something's motion, then being able to catch it would be a good test of how much motion you're feeling. So somehow velocity, how fast that object is moving, is related to its quantity of motion. Now, that's not the only aspect, though, because I couldn't just throw any object at you and it would be easy to catch if it was slow, right? If I took, say, a bowling ball and threw it slowly at you, it would be pretty hard to catch, right? Why is it hard to catch? Well, because of its mass. Because that object, that bowling ball, has a lot more mass than an apple. So it's going to be a lot harder to catch, even though I might be throwing it slowly. Okay, so somehow then, velocity and mass are related to an object's quantity of motion. In fact, they're the only parts that make up an object's momentum. The equation for momentum is pretty simple. We use the letter P to represent momentum. That confuses a lot of people. Why the heck would we use P? P is not even in the word momentum. Well, actually, when Newton originally came up with the concept of momentum, he used a different word to, he called it a different name. He called it impetus. And so when he came up with the original mathematic variable for it, he looked at impetus, the word, and said, well, I is taken for imaginary numbers, M is taken for mass, so I guess it's going to be P. And that has stuck with momentum since. So, momentum is the letter P equals an object's mass times its velocity. Simple as that. It's just its mass times its velocity. So let's say we were to have a 2,000 kilogram car. So we got a car driving down the road. Let me see if I can draw a car real quick. Okay, I've drawn better cars. So the object's mass is about 2,000, and its velocity is 23.45 meters per second. Okay, so question is, how much momentum does this car have as it's driving down the road like this? Okay, well, momentum is just mass times velocity. So we take the mass as 2,000, and the velocity is 23.45. Multiply those two together, we get an answer of about 46,900. So now's a good time to talk about units. We haven't discussed the units of momentum yet. Let's look back at our equation for momentum. Well, mass has units of kilograms, and velocity has units of meters per second. So if we're multiplying those two together, then our answer, our units for momentum, are going to be kilograms meters per second. I wish there was some other name that we could give it than kilograms meters per second, because it's a little bit of a mouthful, but that's just what it is. That's what they're called. So we got to stick with that. All right. So that's helpful and all. Understanding an object's momentum is useful, but it's more useful when considering collisions. That's what we talk about in physics a lot. When we have two objects hitting each other, we call that a collision. It's just two objects hitting each other. Now, we did a lab in class where you guys collected some data on the velocity of an object before and after it hit another object of the same mass. We had those carts on the track, and we were seeing how did that initial velocity change the final velocity. So let's consider the momentum before and after the collision, and you'll see something pretty interesting. So let's split our paper in half here, and I've got some student data here where they said their initial velocity of their cart was approximately 1.42 meters per second. And then after the collision, the velocity of the cart after it hit and stuck to the other object, it was about 0.73. Okay? 0.73 meters per second, that is. So let's look at the the momentum of these objects before and after the collision. Well, in the case of this cart over here, I measured it as a mass of 0.255 kilograms. All right? So momentum is just going to be mass times velocity. So it's going to be 0.255 times 1.42. Okay, so let's see what we get here. Plug it into my calculator real quick. Our answer here is going to be 0.362 kilogram meters per second. Okay, and then let's look at the momentum over here. Now, after the collision, the two objects hit each other and stuck together. So when I'm considering the mass of the object, I'm going to kind of pretend like the two carts stuck together is one object, and I'm going to use 51 kilograms as the mass, because that's just one of the cart's masses doubled. Okay? So here we go, solving for the momentum. It's going to be 0.51 times the velocity of 0.73. Plug it into my calculator. Let's see what we get. I got approximately 0.368 kilogram meters per second. Now, what's interesting about this? Well, these two numbers are almost the same. They're pretty much equal. And that's what's interesting about momentum in a collision. This is something called conservation of momentum. And it states that momentum in a system is always conserved, meaning it always stays the same, as long as there are no outside forces. Momentum in a system is always conserved, meaning it always stays the same, as long as there are no outside forces. Okay? So that's kind of our rule to this law of conservation of momentum. There has to be no outside forces, meaning get rid of friction or some sort of other thing that can influence the force on the system. As long as there's none of that, momentum is conserved. It's going to be the same before and after. Okay. I'm going to essentially rewrite that as an equation now. So basically what we're saying is that the momentum before a collision is equal to the momentum after. Okay? And I could expand that out to a much more helpful equation here. We're mostly going to deal with collisions between two objects in this class. So the mass of object A times its initial velocity plus the mass of object B times its initial velocity equals the mass of object A times its final velocity plus the mass of object B times its final velocity. There you go. I've essentially just rewritten conservation of momentum as an equation, and it's this right here, and it's going to help us a lot when we are trying to solve for these different types of collisions and understanding how much velocity objects have before and after those collisions. All right. Speaking of collisions, there are two types of collisions we deal with in this class. We deal with elastic collisions. Oops, spelled that wrong. Elastic collisions and inelastic collisions. Okay? Now, in elastic collisions, the objects bounce off each other. In inelastic collisions, the objects stick together. There are other factors that distinguish elastic and inelastic collisions, but we don't really need to get into them for this class. For now, let's just say elastic, they bounce off, inelastic, they stick together. All right? Let's do a quick example using conservation of momentum. Let's say that we have two toy train cars. There's one, there's two. Let's say this is car A, this is car B. Has a mass of 3 kilograms and is currently moving towards car B at a velocity of 1.4 meters per second. Car B has a mass of 4 kilograms and is actually, it's at rest right now. It's not moving at all. Okay. And the question is, when they collide, when the two cars stick together, hit and stick together, what is their final velocity going to be? Okay. So here's how we deal with this. We're going to write our conservation of momentum equation. On the left-hand side, we have the momentum, the initial momentum of car A plus the initial momentum of car B, and that equals the final momentum of car A plus the final momentum of car B. So looking back over here, we have a mass of 3 kilograms times a velocity of 1.4 plus car B, well, it has a mass of 4 kilograms, but it isn't moving. Okay. Now over here on the right, because they collide and stick together, I'm going to use a little trick here, and rather than considering the two objects as separate, I'm going to pretend like they're the same object. To do that, I add their masses together and give them the same final velocity, which makes sense. They're stuck together. They have to be moving at the same speed. Okay, so let's solve for this then. 3 times 1.4 is going to be 4.2 equals 3 plus 4 is 7 times VF. Divide both sides by 7. Our answer is going to be 0.6 meters per second. So that is how fast the cars are going to move after they hit each other, stick together, and move off. All right? So there you go. Those are our notes on momentum. Hope it was helpful. See you guys later.